So in this PowerPoint, I'm going to go through the differentiation of inverse trig functions. So when I say inverse trig functions, I mean things like this: inverse sine, inverse cos, and inverse tan. So the ones where you press shift on the calculator. Now, not only do you need to know what the answer is when you differentiate these, but you also need to know the proofs of them as well. Now, the three proofs are quite similar, so once you know one, you sort of know them all, but we need to go through the proofs now of how to differentiate each of these. So let's start off with this one, y equals the inverse sine of x. Now, using what we already know about differentiation, we know how to differentiate sine, but we don't know how to differentiate inverse sine. So what we could do with this is we could perform sine to both sides of this equation. And if I do sine to both sides, on the left I'll have sine of y, and on the right I'll have sine of inverse sine of x. And the sine and the inverse sine will cancel each other out. Or, if you want to simplify that, you could just think that I have taken this inverse sine over to the other side and made it a normal sine. So I've got sine of y equals x. And then I tend to just flip that around and write it as x equals sine of y. So now it looks a little bit simpler, looks a bit easier to differentiate, because now I haven't got to differentiate an inverse sine, now I've just got to differentiate a sine. Now you've got to make a decision what you're going to differentiate with respect to, because you've got to make sure you do the same on both sides. So I'm going to choose to differentiate each side with respect to y, because the more complicated bit is the bit that has the y's in it. So I'm going to differentiate both sides with respect to y. Now let's look at the right hand side first, because that's easier. Sine becomes cos. So sine y becomes cos y. On the left, if I want to differentiate x with respect to y, I could write that as dx by dy, because I'm differentiating x with respect to y. So that's what we call it, dx by dy. Now, if we think back to the beginning of the question, our aim was to find dy by dx, because we wanted the differential of this, y equals inverse sine of x. So we wanted to find dy by dx. Looking at what we've got here is pretty close. The only problem is that it's upside down. So what we can do now is the reciprocal on both sides, or in other words, flip both sides upside down. So now, instead of it being the wrong way around, it's the right way around. So we've got our dy by dx on the left, and then we've got 1 over cos y on the right. So we've now got an answer for what dy by dx is. The problem that we've got now is that this is written in terms of y, and we don't really want our answer in terms of y, we want our answer in terms of x. So we've now got to find a way of replacing this bit on the bottom with something to do with x. So there's a little trick with this. Remember that cos squared plus sine squared always equals 1. We learned that last year in AS. So if I write it with y's in, cos squared y plus sine squared y equals 1, I can then rearrange this to get cos y on its own. So I could take the sine squared y over to the other side, so it becomes 1 minus sine squared y, and then I could square root both sides so that I can find out what cos y is. Now the reason I'm doing that is because I want to try and replace this cos y. So from this I know that cos y is the same as the square root of 1 minus sine squared y. So I could put that in. Instead of cos y on the bottom, I could write square root of 1 minus sine squared y. And then that's handy because we know something about this. Look back to earlier. Sine y was x, so sine squared y must be x squared. So I've got a final answer of 1 over root 1 minus x squared. And this is the answer that's in the formula booklet. So it tells you in the formula booklet that when you differentiate inverse sine of x, you get 1 over root 1 minus x squared. Now there's only one thing that we haven't mentioned, which is really important, when I took the square root of cos squared to make it a cos, I wrote the root sign in, but I didn't give any thought as to whether it would be the positive root or the negative root. And that's something that's very important that we should give some thought to. So why is it correct to take the positive root, as I did automatically? Why wouldn't it be the negative root? Well, I think the simplest way of answering that is to look at the graph of inverse sine. So on the next slide now I'm going to show you what the graph looks like, and then you'll see why I took the positive square root. So this is the graph of the inverse sine of x. So you can see from the graph that it's always going upwards. The gradient along the graph, wherever you choose a point along this graph, the gradient's always positive. So I think that's the simplest way of explaining why we've taken the positive square root. It's because the gradient of this graph is always positive. So have a go now at proving this one. So the differential of inverse cos. The method is almost identical to the inverse sine proof that I went through a couple of slides ago. So use an almost identical method to see if you can differentiate inverse cos, and then when you get an answer you can check it because it's in the formula booklet. Here are the three graphs for inverse sine, inverse cos and inverse tan. So you can see that the two on the left are both positive gradients, so they both have positive differentials. And then the inverse cos graph is going downwards, so this one always has a negative gradient, which is why the differential of that one has a minus in front of it. Okay, so we've just proved that when you differentiate inverse sine, it becomes 1 over the square root of 1 minus x squared. Now in this question, rather than just having inverse sine of x, we've got inverse sine of 4x. So the first thing I'm going to do is just copy this formula, but where I see the x, I'm going to write 4x. So it starts off looking like this, 1 over the square root of 1 minus 4x squared. And then using the chain rule, I also need to differentiate the 4x. So if I differentiate that, I get 4. So my final answer will be 4 over the square root of 1 minus 4x squared. The second one's quite similar. So we've just proved that when you differentiate inverse cos, you get minus 1 over the square root of 1 minus, and in the formula booklet it says x squared. But if we apply that to this question, it's not going to be x squared. We need to write 5x squared, and then we times by the differential of the bracket, which is 5. So this one becomes minus 5 over the square root of 1 minus 5x squared. If you really wanted to, you could change the denominators into root 1 minus 16x squared, and this one would be root 1 minus 25x squared. So you can square out those little brackets if you want to, but you don't necessarily have to. Okay, so now I'm going to go through the proof of inverse tan. It's slightly different to the inverse sine and inverse cos, but it starts off in the same way. So I could take the inverse tan over to the left hand side, and then that's going to make it tan of y equals x. And then I tend to flip that around so it's x equals tan of y. And I'm going to differentiate both sides with respect to y. So far it's the same as the inverse sine and inverse cos methods. So if I differentiate both sides with respect to y, the left will become dx by dy, and the right will become sec squared of y, because if you differentiate tan, you get sec squared. Now we learned a trig identity this year that had a sec squared in it, and the trig identity was that sec squared is always equal to 1 plus tan squared. So that's the trig identity that you should know already. So we can replace this sec squared with 1 plus tan squared. And the reason that that's useful is because tan of y had a name earlier on. Tan of y we knew was equal to x. So this tan squared y we can now replace with x squared. So we're putting it back in terms of x rather than leaving it in terms of y. Now there's only one other thing that needs to be done, and that is to do the reciprocal, because this dx by dy is upside down. So if we flip it over, we get dy by dx, that's what we were aiming to find, which means that we'd also have to flip over the 1 plus x squared, so it becomes 1 over 1 plus x squared. So when you differentiate inverse tan, you get 1 over 1 plus x squared. So here's some questions I want you to have a go at. Press pause now. I'm going to start writing some answers on, so make sure you press pause so you can try them before I start putting answers on. And finally then, here is another reminder of the formula booklet. There's a whole page dedicated to differentiation. You've got your quotient rule at the top, then you've got some trig, tan, sec, cot and cosec, and then these three on the bottom, the ones that we've covered in this PowerPoint, of how to differentiate inverse sine, inverse cos and inverse tan.